to take a minute to say thank you to Xylem for sponsoring this panel. And unfortunately, because of travel restrictions, Luis, who was also moderating with me, is unable to be here. But you know, we will definitely have his slides on the website when all of these presentations go up. So today we're going to be talking about digital twin. Let me just make sure I got this right. Yeah, the challenges and benefits for the water sector. And I want to introduce our panelists right now, and then I'm going to give a brief introduction to what I mean, or what we mean by digital twin. There's a lot of ideas and definitions for it, but here are some of the ideas. We have Biju George from DC Water, Cecil McMaster from New York City DEP, Pilar sorry, from Global Omnium, and I hope all of you have actually seen the Global Omnium Digital Twin, and Sri Kamojjala from Las Vegas, Nevada Water District. So I look forward to hearing what they have to say, and I think we're going to all learn a lot from their experiences and their wisdom and their vision. So here is a quote from Colin Paris. He was a VP of software of GE. What he thinks of a digital twin is a living model that drives outcomes. And I think you're going to actually hear about that from the panelists. Whoops, sorry. Let me go back. Okay, so what do we really mean by a digital twin? Really, it's a software model that emulates the physical system, whether it's a pump or a larger system like a whole utility. And it's a model that uses data as input from the real physical system, as well as the model that emulates the behavior of the physical system. And then we run simulations that accurately represent what's happening in the physical world. So that's really the concept of a digital twin. And it's an ever-evolving concept. It's not like a utility can go out and buy a digital twin and hook it up and it works. It's a constant evolution where you're constantly looking at data that you're collecting from the physical system and evolving the model, adding machine learning to fill in some of the gaps where the model is not considering some of these areas. So as you continue to build your digital twin, it will become more and more accurate to your physical system. And then it really becomes a very powerful tool that you can use in operations, in predictive analysis, in your business revenue predictions. It's very powerful, especially in operations. It can give you information about the slightest anomaly before that turns into into a failure. So it's a very, very powerful tool. So I have, let's see, this is a video that I saw on LinkedIn and I fell in love with it. It shows earthquakes for the last 100 years, since 1901, and the data that we've collected, and it shows the size and the depths based on the color and the size of the circles. And over time, you can see the year down there, what's happening. And eventually, because you're going back, you're stepping back, and you're looking at holistic data, you can start to see what's really happening with the planet Earth. And it's all the earthquakes seem to happen in a way on these tectonic plates on the Earth. And then eventually, you start to see a picture that we might have not been able to see before when we were just looking at one earthquake here or one earthquake there, looking at different sizes. With all of this data, you can start to model, and hopefully in the future, we'll be able to predict exactly where the next earthquake will happen, and the size, location, depth, everything because of this data and this view. And in a way, I think this symbolizes what digital twin technology can do. It gives you more of a holistic view of what's really happening in your system. So I think I will move on. I don't know if I have to wait till the end. But you see all it's almost like cracks when you crack an egg. There's certain areas where all the earthquakes happen. And you know, we've been seeing earthquake on the news and reading about it, but to see it visually like this and what's really happening is kind of cool. All right, is there a way I can, okay, I think it's done. So, all right, so to bring it back to the context of a water utility, you know, today water utilities have different vertical systems, different system for administration, like a SCADA system, a CMMS system, a CIS, a GIS. And as we've been talking about in this, this workshop, in this conference so far, a lot of that data is siloed. So really, to build a digital twin is to bring all that data together, use the hydraulic model, which all utilities use for engineering and expansion, but start to use it in a real-time mode, and use real-time or near real-time data from the actual physical utility, and run the simulations and get the results that we're looking for with a digital twin. So that's kind of giving you an idea of what we need to do in terms of water utilities and building the digital twin. This is not an easy proposition. It's very difficult, and this is a technology side of it, but a good portion of it, maybe even 60%, is the people side and the process. And I'm sure we're going to hear a lot from our panelists about that. Okay. All right, and I just want to mention that a digital twin could also be used in the design phase, using BIM, building information modeling, carry that all the way through construction, and hopefully continuing to keep the same BIM information into operations. This is not really being done today in most utilities, but I think we would all benefit if we start thinking of digital twin in the early stages of the design. And lastly, I want to talk about when we're talking about the water utility space, I consider a digital twin of a drinking water utility, a digital twin of a wastewater, a digital twin of stormwater, and a digital twin of source water. And eventually we can concatenate all of these digital twins to better inform the next digital twin down the road. So I think eventually this is the water cycle that we would be able to follow with digital twin technology. And the vision is to follow a water molecule all the way through the cycle by really understanding where it's going at all times. Lastly, about a year ago, I started a digital twin working group within the SWAN organization. We are focusing on the challenges of digital twin, and together as a global community, when we want to find the best practices so that we can accelerate the adoption of digital twin in the water sector. So I would invite all of you to participate and join us for the SWAN conferences and workshop. So thank you so much. And now I will give it to Biju George for his. Thank you.
Thank you, Gigi. So Gigi asked me to cover the challenges and benefits of digital twin from a leadership perspective as an early adopter. So I did not get into digital twins by aspiring for building a digital twin, but was trying to solve a problem, then tripped my way into it. So I'll start with the first story. I would like to recognize my former colleague, Ryan Welsh. Where is he? There he is. Okay, yeah, so it's a story from my, before I joined DC Water. I had Ryan's role in Cincinnati, and then Cincinnati was faced with a massive legacy issue of combined sugar overflows. And we had to come up with a solution other than a tunnel as a solution. So we had to redefine the problem and come up with one. So this is where the challenge was, okay, how can you really find capacity, available capacity, and maximize it? So the way how we did was, using the Doppler image and then trying to see if we could predict at least 2 years in advance what's the hydraulic gradient would look like in a manhole, and then can we maximize the available capacity. That was kind of the introduction to it, and then from there, Cincinnati has taken it, and then probably has one of the best smart sewer system that at least I know of currently, maximizing the capacity and bringing the benefits to the combined sewer overflows. So the lesson I can share with you all is if you're trying to find a a digital twin solution, pick up your biggest problem and then trying to find a technology solution to deliver the benefit for it, as opposed to trying to adapt a twin and then try where you can create value. So, what you're looking for is real. So these are some of the examples that at DC. There are many. I just wanted to briefly touch on the water age and pressure management. That's the easiest one. Once you have a calibrated model, you can easily simulate and manage that. Especially since the consumption patterns are changing and slowing less usage. So you have to manage the water age. So that's the best use we have of the hydraulic model. And the other one is at DC, about 3,000 meters. That accounts for almost close to 40% of our $600 million revenue. So those are extremely critical. So in the past, it took us almost 2 years before we identify any issues with the meter and then take it to the shop and then recalibrate and then change it all. And then so by closely mimicking what the meters are and the consumption pattern, now we are able to identify that the challenges or any degradation in the meter in less than a week, and then manage to take care of that. So it's a significant contribution from the perspective of value creation. The next one is the source water monitoring. Because this is from the perspective that we have only a single source. If anything happened to DC source Potomac River, we have less than 36 hours of water. So it's extremely critical to keep nation's capital in DC, in the United States, with quality water of sufficient capacity. So we do have monitors, and also we have continuously tried to simulate, what a plume model could look like under varying weather conditions. So in case anything happens, we can truly monitor and manage between the two intakes how such things could be avoided. So those are some of the examples where we really applied, the very close simulation, so we can find the most value, because some of our biggest problem. So in terms of is some of the lessons learned as a perspective for those who are trying to either get in or already in and then trying to figure out value. The first one is, instead of trying to, build an identical twin or very, highly correlated, model, it's a focus on creating value. The moment you start, you can find that there are course values you can identify early on, and as you start using and more maturity, you can find more and more value. The second one is finding the right talent to manage that, because it's just to give an example, because when we were looking into creating the digital twin or managing the smart system in Cincinnati, rather than trying to find an engineer to do it, I reassigned at that time who was CIO to manage the engineering project, because who wasn't afraid of the technology, and then much easily adapted to engineering and then built the solution. Same thing, because even in DC, I look for graduates with a computer as well as technology background, so we can maximize the benefit from it. The third one is if you can find a near-term forecast with whatever tool you develop, which means if you can use that for short-term planning on a regular basis, from the information to your work, you're easily going to mature such models, and then the utilization of that going to expand, and also you will end up with a much valuable product. And finally, this is a big one, because if you maintain or leave the existing infrastructure and then expect that to behave something other than, not infrastructure, organizational structure, and them to behave differently than the silos they're already in, it's not going to happen. So you have to reorganize your organization to function efficiently, and then the deliver value you're expecting. So DC, I'm really reorganizing the engineering into 3 different organizations. The one that will be asset management and smart technologies, with their focus that future solutions will be really focused on the principles of asset management as well as leveraging the technology. So those are some of the perspective from me, and then I will look over your questions and then engaging on a dialogue. Thank you, Cecil.
Hi, good morning. Again, my name is Cecil McMaster. I'm the Chief Information Officer for New York City Environmental Protection Agency. And I'll talk a little bit about the agency and then talk a little bit about our digital journey, because digitization for us has been an ongoing thing, right? I mean, in most of these large organizations, especially utilities, we have been using computers and digital input and output for a very long time. So I'll talk to you a little bit about what we're doing, some of our projects that we're in, right? But just a little bit about the agency. The agency will manage the water supply system, so we bring about 1 billion gallons of clean water down from the Catskills, about 125 miles down, 99% of it through gravity. So it's a gravity-based system. We pump probably less than 1% of water in one high elevation in Manhattan. But 90% of the water, 99% comes down through gravity. It takes about 30 days from the source to get that water down into the system. We have 19 reservoirs and 3 controlled lakes that we mix the water from. So depending on what's going on in the different reservoir systems, if there's storms, if you have bad quality water or turbidity, we could take a mix from the different reservoirs and the lakes to get the best quality of water down into the system. We cover about 2,000 square miles a land, right, in terms of around the reservoir. So it's a huge system we manage. And then we have about 7,000 miles of water mains that distribute that clean water, potable water, for about 9.5 million people in the city. So a large system. The other thing that makes this complicated is the system is over 130, 120 years old. So it's an old system, a lot of old capital infrastructure that was put in many, many years ago. And one of the problems with these large capital infrastructures, a lot of those money was funded, a lot of those projects were funded years ago by the federal government. And then they left it up to the states and the cities for maintenance, which made it complicated. We don't see a lot of large investments in the old infrastructures anymore. So that makes this difficult. We treat about 1.3 billion gallons of wastewater in the city with 14 wastewater treatment plants. So after that water comes down and is used, we treat about plus with the storm water, about 1.3 billion gallons. And we move that stuff through the system with about 7,500 miles of pipes. We're also responsible for air and noise mitigation. So we have hundreds of thousands of sensors in the 5 boroughs in the city that we constantly collect, from water metering to air quality samples to noise. And we work with the industry to help to remediate those systems. And all of that data is fed back into databases that we host and try to use the data to help us with the operations, right, and remediation for the process. This is just a map of the system. You know, if you look, like I said, we bring the water from about 125 miles up all the way down into the city. And along that journey, We do a lot of sensing. We have sensors all throughout the system in the reservoirs to make sure that we're monitoring the quality of the water. We look for contaminants in the water, right? We have pressure zone sensors that would tell us what's going on with the pressures in the water. So we've been collecting this type of digital information for a long time. The difference now is that we're using that data to help improve our operations and how we deliver the best quality water for the constituents. This is a control system for the controlled water supply. And this system was put in 2003. We're still using it today. We're in the process. We're on like a 10-year journey to really digitize the whole water system from the source to the treatment in the city. So we are on that journey now where we want to tie these systems together to start to integrate the data so we could make more sense and start doing predictive, prescriptive. We use 100-year precipitation models to help us run the reservoirs at different levels. If we run the reservoirs too high, there's a potential for flooding. If you run them too low, there's a potential for drought. So we are constantly modeling from the weather source, right? And this is the control center where we make operational decisions. We know how much water to release into the city. We have to model because it takes about 30 days from the source. So we are constantly modeling based on the usage. So you would figure out in the mornings, we would push more water through the system. About lunchtime, we're pushing a little bit less than we did in the mornings. And then in the evenings, so we are constantly modeling that stuff to know how much water to produce. And that stuff is monitored and controlled from our water supply control center, which is about close to the source. We're about 100 miles upstate that we run that from 2 sites on. And this is just an example of what the guys see from the different system. And that's a real-time model on the levels in the reservoirs, the heights in the reservoirs. So we have people constantly looking at that on a daily basis, 24/7. And we use those outputs to make decisions on where, based on the quality of the water in the different reservoirs, on where to take the water from. Again, on the wastewater treatment side, right? When we talk about digital twins, we have 52 different SCADA systems. I mean, some of our plants are over 40 years old, and you have thousands and thousands of sensors and old systems. And it's not easy to replace these systems because these systems control critical treatment processes. And if you're going to replace the system, you really have to look at the processes. And the 14 treatment plants were built over the last 50 years, right? We have our newest plant came online in I think it was 1986 was the treatment plant. We had a water treatment plant that came on in 2011, 2012. But the newest wastewater treatment plant was in 1986. So you see how old these systems are and complicated. And we have 14 in city, but we have another 7 upstate wastewater. So total of 21 wastewater treatment plants. Now, to build a digital system that mimics that whole system is complicated, right? We're on the early journey we did last year. We did workshops in the 14th in-city treatment plant with the plan to reduce the number of systems, right? We would like to get to half of the systems that we have. But it's a huge capital investment, when we're looking at a 10-year, probably $3 billion project, right? To really start to optimize and modernize some of these systems in the plants. So really complex. And then this is the wastewater treatment stuff. They're pushing me along. This is just a model of the sensors here, where we have sensors in the city. And another, the plan in terms of a digitization is to get from all of our plants into a single control system where we could see a model from the source all the way down to to our customer's house, that we know what's going on with the system. And then the most important thing, we can't do this stuff without people, right? So people are the most important thing, in terms of doing these systems, right? And I want to leave with that. We are on this 10-year vision that we're going to try to complete that. And that's kind of where we are. Thank you so much for your attention.
Good morning, everybody. It's a pleasure for me to be here in this panel with all of you. We are going to speak about challenges and benefits for digital twin. As Gigi said before, what's a digital twin? A digital twin is a virtual copy of our real system that represents behavior and serves as basis for experimentation. This is very important because we can test new ideas, new changes in our virtual copy before making a decision in the real system. So we can minimize a lot our risks. So with a digital twin, we can monitor the whole system. We can analyze its behavior. We can simulate its behavior under other conditions, what-if scenarios. And finally, we can improve its performance. But what do we need for developing a digital twin? For developing a digital twin, we need several things. The most important thing, we need information from the real system. So a data-centric platform that integrates all the information coming from the real system, it will be very interesting and useful and necessary. We need also hydraulic models in order to simulate the behavior of the system. And also, we need another analytical capabilities like machine learning that they are going to be very useful also. The digital twin finally has to be continuously paired and connected with the real system and has to be calibrated in order to behave like the real system, like the physical world. For developing a digital twin, really we have to follow several steps. The first step is to define the scope of our digital twin. As Gigi said before, we can develop a digital twin for the whole water cycle, or we can decide to start with a digital twin for only one process of them. In our case, in Global Omnium, we decided to have a digital twin first for the water distribution network. Once we have defined the scope of our digital twin, it's very important to define our objectives. What are we going to use the digital twin for? In our case, we decide to use the digital twin for long-term planning and also for help us to make decisions in real time in the daily operation. We wanted to have a digital twin for help us to develop our master plans, considering the extension of the network, the replacement planning also, and the necessary investments to increase and improve the resilience of the system. But we wanted also to have a digital twin for help us in the daily operation, for helping us to make the best decision at any time. So we use nowadays the digital twin for help the best decision under emergency conditions. It's very important. We use it also to plan special works in the network that at first could affect the customers. And we can plan the best time and the best operation in order not to avoid the customers. Finally, we use it for improve the performance of the system. Once we have defined the scope and the objectives of the digital twin, we have to, on the next step, is analyze the information that we have from the real system and the information that we need. Actually, nowadays, most utilities have the necessary information for developing a digital twin. because we have nowadays GIS, we have SCADAs. It's true that we have maybe several SCADAs. We have billing systems, more recently smart meters, and we have systems to manage the maintenance of the network. So a digital twin needs information coming from these different sources. Then the first step that we have to do is develop a big data platform that integrates, concentrates, and normalizes all the information coming from the different systems. And then, so we are going to be able to develop the digital twin, taking all the information in this platform. But not only technology. The culture and the organization is also key for deliver really very quickly results. It's very important, the constant collaboration between the different departments, because the digital twin involves different people, different departments in the company. It's very useful to have a new agile organization, and obviously it's very useful to foster an open, innovative culture. Why? Because digital twin, as other disruptive technology, at the end, people has to adopt it. And finally, the last step is to develop and add analytical capabilities to the digital twin. In this stage, a hydraulic model is going to be very useful, because a hydraulic model allows us to simulate the network behavior under any condition, even if it happens or not. But for being really useful, this hydraulic model has to be accurately developed, perfectly calibrated, and updated. That means that we need a hydraulic model running in real time. So we are going able to simulate what's happened right now, what happened yesterday, and the most important thing, what could happen in the next future. But not only hydraulic models. We can use also other data advanced analytics like machine learning, artificial intelligence, and then all the potential of the digital twin really can be exploited. In our case, in digital twin, in Global Omnium, we manage a digital twin for the water distribution network that supplies water to Valencia and its metropolitan area. This digital twin contains 900 kilometers in length, more or less 10,000 pipes, and the main regulating elements like tanks, pumps, valves. Our digital twin works upon a hydraulic model that is running in real time. Is connected with more or less 600 variables in real time. 20% of them are imposed, are settings, and 80% of them are used for calibrating and validating the model. Finally, really a digital twin can bring us a lot of benefits, opportunities, because as I said before, we can try new ideas, new changes in the real system, minimizing a lot the risks and the cost. Really, having a digital twin is a challenge, but we have to say that today the technology makes it possible. Thank you very much.
Good morning. Bring the slides up. So what I'm going to talk today is digital twin for water utilities. More specifically, how we applied at Las Vegas Valley Water District since 2005. Sorry. Let's do it quick. So if we take any utility, we have three, or any business, you have three functions. One is taking care of your existing customers, which is operations, and taking care of future customers, which is system growth, and taking care of your assets, or asset management, or infrastructure management, whatever you call it. So you need to integrate these three functions for most efficient functioning of your utility. So you have to, basically, the ultimate goal is to make quality of life better for your customers at reduced cost to your ratepayers. So again, if you take a utility, you have several information sources. So you have spatial or GIS data, you have physical or data models, right? And then you have SCADA or sensors information. And also you have enterprise or corporate data, where you have all the customer information and so and so. For users to make decisions, they have to integrate information from all these sources. The reason we are able to do things that we can do now is the advancements in technology, right? You can integrate information easily, so you can do things, more things than you can do before, and then faster. So, okay. So again, the benefits of integration, right? If you can see manually integrating this data. I'm going back to 2005, bringing information into model from your SCADA. It would take forever, right? But with the click of a button now, you can bring all the information. So it enhances the data accuracy and then obviously efficiency. So what we did when we looked at this, we said the user, when they want to make decision, right, they only need to worry about what data they want to see and what format they want to see. They should not worry about where it is stored and how it is stored, right? So to integrate it, you need to have a user interface or digital twin. That's what we call it now. So we put a user interface, and then user interacts with all this information and how they want to see it. And then that's the digital twin that we created. So I'll show some examples. So the way it works, so we have these integration of functions, right? So if I take asset management and operations, I get increased operational efficiency. And if I take between assets and my system growth, then I have cost-effective infrastructure, right? So that's the ultimate benefit. And then you have to see how is this digital twin that's sitting in the middle, right? And then with the data analytics, integrated analytics, or AI, whatever you call it, how is it going to impact all these functions, and how am I going to integrate, right? So every utility has their own benefit, right? There are certain benefits that our panelists pointed out. You have to see what's the biggest the benefit, right, the problem, and how do you tackle that problem in the most efficient way. So a couple of things I want to cover. A lot of times, you say, okay, what's the sensors versus physical models, right? So what's the benefit? If you look at to the left here, I have SCADA, and I have 7 points. And then to my right, I have our all pipes model, which I have 220,000 pipes. So just to give you a brief introduction of our system, we have 5,000 miles of pipeline, more than 5,000. And we have close to 300 pumps. Our demand goes from 180 MGD to 450 MGD in the summer. So we need to basically operate this, everything optimally. So I have 7 SCADA points. Now, if I calibrated a model, I have 20,000 nodes to the right in my model. So I can make that predict what's happening at 20,000 locations in my model, right? That's just a portion of our system. And so so I can extrapolate spatially, right, with the physical model. And then another here, what I have is SCADA can tell you what happened and what's happening now, right? It cannot tell you what happens in the future if you want to make some policy decisions. So what I have there is I have reservoir level, right? It can tell me what's happening, to that point in the past. But if I want to predict with certain, operational policies, it won't tell me. So the benefit of having a physical model is you can extrapolate spatially and into the future, right? And again, depends on what you're trying to see. If you're only interested in what's happening current system, you can make decisions. Maybe sensors are fine, but most of the time, I think you want to see what happens in the future. And again, a lot of times say, what detail do I need, right? So to the left, we have a skeleton model, which I have over 10,000 or 11,000 pipes now. And to the right, I have the 220,000 5 model, right? So what do I use this for, right? If I have an operational model that I'm trying to predict a pumping plan, what I have to the left is good enough. But if I'm trying to do water quality or shutdowns, right? If I'm trying to see what happens, then what I need to have, what to the right. So we use both of them in different scenarios. Okay, again, these are some of the benefits of digital twins. So I'll show you examples. We started with as a water quality and energy, right, back in 2005. But these are all the benefits that we saw, most importantly, emergency response and asset management and protection. A lot of times that's lost because you save a lot of money, in those areas. Okay, so I'm going to give you an example. So what we did back in 2005, we needed to optimize energy and water quality. So we started developing a daily pumping plan. So the way it works is we download the current system conditions from SCADA, and we project an operation daily pumping plan to run the system for next 24 hours. And then that plan is pushed. It is done by our operators through using our hydraulic model. And then we have tools I'll show you in a minute. We push it to run the system to SCADA, actually to a database. Then it's pulled into a SCADA system by operator for security. And then the system is run next 24 hours. And so if you, one of the things that you need, right, to make this happen, like again, the technology. So if I had to do this manually, at that time we had 260 pumps, right, 252. So every pump, on and off, even one on and off, you're looking at about 600, right, typically controls. For them to do it manually is just impossible. That takes a lot of time, right? We had to do this plan in 1 to 2 hours. So we developed a tool so that looks like a spreadsheet. So to each row is like a pump, and then you have 24 hours of operation. 0 means off and 1 means on, right? They can pick a bunch of pumps and put a predefined pumping pattern. They can also pick whole pressure zone and then say, I want all these pumps on certain pattern, or you can pick a pumping station. They can also, what we ordered power, they can compare and see how much power they're using. And as they're making changes, they can see the reservoir levels, right, how they change. And also the tagged out pumps. So this is coming from SCADA. They can see which pumps they cannot use. That yellow line is the tagged out pump, right? And so that's the reservoir level. So they can compare too, right? As they're doing it, they can compare predictor versus model. I'm showing this end of the day, but they can do any time in the day and see how it compares, right? And so here's the result, right? You see what you see on this graph is the bars are the elevation, average elevation that we pumped water to, right? And then the line, the black line or blue line, whatever it looks, it's the kilowatt hour per million gallons, the energy that we used, right? So we started this in 2005 July. The pumping, sending a daily pumping plan. And you can see these 6 months, we saw the benefit, right? By the time we did the whole year in 2006, we saved 15% in energy. We use about $12 to $15 million for our energy costs. So we pump from 1180 to 3665. And also the other thing that I'm not showing here is the graph where our water quality actually significantly improved. We store less amount of the water storage time, drastically reduced, and then those are the benefits, right? One last example, I'm going to show the other benefits. Okay, so these are what we started with, but you'll see the main.
It's hard.
So the one of the side benefits, right, or the main benefits, the way I see it, is the emergency response and asset management or prediction. So here I have a tank that's shut down, right? We lost, let's say we lost that tank. So if I lose that tank, if I will lose all those red spots, I won't have water, right? Green means it's good. So I need to pump directly into that system without the reservoir. And many of you know in hydraulics, the pressures will be vary, right, with the demands. So I need to know how to run this system because, like I said, our demands vary during daytime tonight. So I need to run, I have 5 pumps, right? I need to run anywhere from 1 to 4 pumps, right, depending on the demand. How do I know? If I don't know, going blind, the operator will run 3 pumps and then, you'll have another issue. So, pipe break, right? So with the model, I can tell, I'm showing you next slide. Okay. So I can tell, that's one of the scenarios for one of the demand conditions, right? I can create this without overpressurizing or not losing customers, right? So depending on the time of the day, I need to run different number of pumps. We have pressure relief valves, but so this is how the operators can quickly see because they already have the system in place, and then they can say, okay, this is what I need to do, and then they know when the demand goes down, what exactly they need to do, and then not overpressurizing the system. So again, with that,
That's excellent. Thank you. So thank you all very much. Those were excellent presentations. I learned a lot, and I'm sure all of you learned a lot as well. So I'd like to open it up to questions from the audience. Well, actually, before we get started, let me ask this question. How many people walking into this room had a really good understanding of what a digital twin was? Okay, maybe 30%, 35%. After hearing some of these presentations, has your knowledge of digital twin improved, gotten more confused, or do you feel like it's something that all water sector utilities have to start working towards? So after the presentations, what's your level of knowledge for what is a digital twin? Is it high? Does everyone feel confident about what they understand about a digital twin? So it was pretty informative. Yeah? Okay. The word twin, it's because just like you have people twins, you have 2 identical. It's the identical version, but it's a digital version of the physical system.
Oh, I see. Okay.
Yeah, there.
It's a version of the reality.
Yes, yes, yeah. Okay, questions?
Good morning to everyone. Thank you very much for all of your presentation. It was very, very beautiful to see all the works that you have been done. But we are talking about digital twins since 2003, 2004, and now is where we see the developments. But what I see here is that we still use trial and error, except this last presentation, to manage our water networks and to manage our digital twin. Okay, it's wonderful, so we can design the entire hydraulic model for the water network. But again, you need very skilled operators, like this girl next to me that was yesterday on the global aluminium water utility, to know how to manage their digital twin and see what happens if we close a reservoir or we close a valve. What I'm asking you, why don't you use optimization algorithms to solve most of their problems? I saw that Las Vegas already does that with the pump scheduling that they show us. But what I can see in main industry, in main water utilities, is that we still use trial and error to see what's going to happen to the water network. And when we have many different reservoirs connecting with each one, if we close one, it's very difficult, even for the most skilled operator, to see what is the best way for us to manage their water network. And I ask you, why don't you use optimization algorithms to help you manage the water network besides of trial and error with very skilled labor? Because very skilled labor in EPANET and similar softwares it's very difficult to find them. That's my question.
Okay, yeah, go ahead. I think you pushed the button. Did you turn it on? The green one, the big one.
Okay, can you hear me? So to answer your question, it's going to be a combination, right? For example, why optimization, right? That you can use. So I'll give you a simple example. I said we have 300 pumps, right? So if you turn on and off one pump, right, a day, right, which we do more than once and on and off. So you're looking at the scale of the problem, 2 to the power of 300, right? If I want to optimize the schedule, right? So to come up with the solution automated on a lot of times people say, I want to do 5-minute intervals, right? First of all, if you have a calibrated model, you know what's going on in your system. You don't need to do it every 5 minutes, because then you're masking the problem. If something there is a really break, 5-main break or something, you're not finding it out, because the reaction would be the more pumps to turn on, right? So because of the scale of the problem, there are certain of them you still have to do a combination of it. There is a place for optimization, where you can do some automation in AI, right, in terms of demands and things like that. But I think it's going to be a combination of some skilled operators. You can reduce the work, right, with the optimization. But the other example I can give you is if you take our system, right, the demand goes from 180 to 450, right? And also we are adding things, and we are taking water at different location, and then our water quality objectives also change. So it's a very complex thing for it to, and then the optimization or AI works better when you have, some trained cases. But every time when you have things change, right, to apply the old solution, we tried some optimization, to just blind optimization, right? It does not give you the result better than what a skilled operator can do sometimes.
That's for sure.
Right. So it's going to be and then this is drinking water. People are drinking. You can't just let it run and then close your eyes, because right. And so it's going to be a combination. Again, I understand what you're saying. You can reduce the effort by optimization, but it's not. It's just a little more complex. Sometimes certain problems, and then systems are changing. So you need to have a combination of those. So we do AI, for example, predicting the demands, neural networks, and then things like that, and then also certain things that we can, automate it, right? In terms of even optimization, we know this is how it can be done. But yeah, it's a combination.
Go ahead, Pilar. Yeah.
Yes, I totally agree with him. As I said before in the presentation, a digital twin is a combination of hydraulic model, but also another advanced capabilities like algorithms for optimizing the performance of the network. I think we don't have to renounce one of them. We can use both of them. Maybe for the daily operation, the algorithms that can optimize the operation can be very useful, but they can work with the simulations. But I think it's very important to be able to try or to test new scenarios by the operators, because maybe in case that an emergency occurs, they have to take the manual control, because in this situation maybe the algorithms they are not going to work properly. It's like a plane. You can have the automatic. You can manual automatically the plane, but maybe when there is an emergency, the pilot has to be ready, has to be prepared, but for taking the manual control and response under this emergency. So I think both of them can work, and we don't have to renounce to one of them.
Did you want to say something?
Sure.
Yeah, go ahead.
So if I may borrow the comment from Dragon Savick this morning, you fly in an airplane that is autopilot, but you still have a pilot. It's very similar, but in our system, first thing is, not everything is fully automated. We still have manual valves, boundary conditions, which we have to worry about, and then especially in DC's case, our water treatment plants are still operated by RB, since we are nation's capital. So coordinating with an operator who is running the treatment plant versus us running the distribution, so there's the manual part of the coordination that's needed. But that doesn't prevent us from looking into the most optimized way of doing it, but still need that manual assurance, because in the end, water companies, we are in the business of, public health, because it's people consume. The second one is public safety. I mean, because when there is a fire, you pull a fire truck right next to a fire hydrant, they have to have water there. So, at least in my case, I don't think I see any time, a machine taking over my system. Yeah.
I would say it has to be combination between the machine and operator.
That's correct.
That's for sure.
Yeah.
Yes.
I'm saying that we have to develop optimization skills to help the operator.
Absolutely.
Because for an operator to know entirely water network, I'm not going to say impossible, but it's very difficult. And when you take the time that the operator really knows the water network, he would get retired because he's old enough and has to rest.
Yeah.
And the new guy will going to take another, 5 years, 10 years, to have the same skills that the operator. It's why we need to develop systems of optimization skills to help those new operators or the old operators to help them. But I agree with you. We always have to have the operator there. Because when a fire happens, there is no optimization or predictive algorithm that can predict the fire. That's for sure.
So the system integration, right?
Yeah.
To make the decisions that they want, to make it easy to operate, that's what we have done. So it only takes 2 weeks for new operators to get trained. And that's it.
So training is easier, even having a digital twin for the training purposes. That could help a little bit. And also, are we finished? Okay, well, I want to give another thanks to our esteemed panelists for an excellent job and very informative. So thank you so much. And thank you all for coming to this panel. Thank you.